So very good morning, children. So this is module number 6, class 12th, subject physics. So this module number 5 onwards we started with chapter 2. So this is module number 6, chapter 2. So the topics that today we are going to learn is relation between electric field and electrostatic potential. The second topic is equipotential surfaces. And the third topic, potential energy of an electric dipole placed in an external uniform electric field. And the fourth topic is dielectrics and electric polarization. So these are actually small topics. So we'll be discussing all these 4 topics in this session. So let's go to the first topic. So the first topic that we are learning today is relation between electric field intensity and electrostatic potential. So before that, let me tell you what do you mean by an equipotential surface. It is a surface every point where every point has the same potential. For example, here the potential is 5 volt. Then here also, suppose this is point A, point B, point C, point D. Every point will have the same potential. Then that surface is called equipotential surface. So I'm going to imagine 2 different equipotential surfaces. So one equipotential surface here, 3D appearance. We need a 3D appearance, so I'm making it like this. Another equipotential surface here. So okay, I'm giving a 3D appearance to this 2 equipotential surfaces. So suppose this is a surface at which every point has 5 volt potential. Suppose this is a surface at which every point has 4 volt, 4.5 volt, 4.3 volt, whatever. But every point has the same potential. So 2 different equipotential surfaces. And I'm going to take one unit test charge. Unit test charge means a charge which has value 1 coulomb, whatever. So a unit test charge, I am going to take this perpendicular to this equipotential surface, and both are parallel, so this will be automatically perpendicular, and the distance between the 2 surfaces is a very small distance, and this distance, these are the notations that I am using from NCERT. We read it like del L. So it is like delta, it is like dl, infinitely small amount. So similar to that. But in mathematics, in higher classes, we learn this is used for partial differentiation. Okay, so del L so let me assume that this surface has a potential V, and this has a more or less, whatever it is, I am writing it V del V, V plus del V. Maybe it is 4, or del V could be minus. If this is 4 and this is 4, 4 minus 0.1, 4 minus 0.2, 4 plus 0.1, whatever it is. So the del V could be negative quantity or a positive quantity. And potential anyway can be positive or negative, scalar quantities. Okay, so relation between electric field and V potential we are going to derive over here, and definitely there will be electric field lines over here, and electric field lines may be in the upward direction or in the downward direction, because electric field is always perpendicular to the equipotential surface. And if it is not perpendicular, suppose there is a surface and the electric field is not perpendicular, suppose the electric field is like this, what will happen? The electric field will have two components, one component like this and other component like this. And this component which is along the surface will, if it is a conductor, just free charge carriers, and it will exert a force on the free charge carriers, for example electrons, and the electrons will move in the opposite direction of the electric field. So there is a drift of electrons. This component E cos theta, I should say. So E cos theta, this horizontal component will drift the electron, and the electron will automatically make an electric current, which is not possible unless you connect it with a battery. So here is no battery connected, still there is a flow of electron, which is not possible. Unless you connect an external source, you cannot make charges flow, because you require energy, an external energy, to be your work done. So to have some work to be done, you require always some energy. Energy is converted into work. So here electrons by itself, electron अपने आप नहीं चलता, और अपने आप इसलिए नहीं चलता because there is no E cos theta here, and if there is no E cos theta, it means there is the electric field must be perpendicular like this, so that there is no horizontal component. So for an equipotential surface, always the electric field is perpendicular to the surface. So electric field is perpendicular here. So electric field is in the direction of displacement here. So what is the work done when you move a unit test charge from this point A to this point B? And the work done is force into displacement. And more clearly, it is force F dot D, F d cos theta. But if the force and displacement are in the same direction, we can write F d cos theta, cos 0, where cos 0 is 1. So we will simply write F d if both of them are in the same direction. And they are in the same direction, because here the force is QE, and the QE is 1 into E here, because Q is unit test charge. And the displacement is delta L here, del L. So the work done is equal to E into del L. Okay, what about the energy here? Because energy is also equal to work done. The change in energy here. So this is a potential V, and this is a potential V plus delta V. So what is a change in energy here? Work done is also equal to change in energy. So V minus V plus del V. Because charges will, a positive unit test charge will always move from a higher potential to a lower potential. So higher, V is higher and V plus delta V is lower. So it will be coming V minus delta V. V cancel, minus delta V is the work done. So minus delta V is the work done, but according to the definition of work done, force into displacement, this is the work done. So you got two different formulas, and you can equate this formula. So E into delta L is equal to del V, which is minus del V, and E is equal to minus del V upon del L. So electric field is equal to potential difference divided by the distance between the two equipotential surfaces. So this is a relation between electric field and potential difference. So potential difference is also denoted in the next chapters by V only. So we can write it like this: E is equal to V upon L. And this minus indicates that, because electric field is a vector quantity and the minus has something to do with direction only. So the minus indicates that the electric field is in the direction of decreasing potential. The minus indicates that electric field is in the direction of decreasing potential. So here in this case, electric field must be in this direction. So there were two possibilities. One is the electric field in the downward direction, but here the electric field is in the upward direction, because this is a lower potential. If it was a higher potential, then the electric field must be in the opposite direction. So so that's all about this relation between E and V's. And the next topic. So the next topic is equipotential surfaces. So if I discuss about a positive charge, what is the potential due to positive charge? V is equal to KQ upon R. That's the formula we learned earlier. So if this positive charge, this is a point positive charge, and you make an equipotential surface, it will have a spherical symmetry, because at this sphere, so I'm writing a positive charge like this. So at the sphere, from every point you can see it will be at a distance r only, because the radius is same. So same potential. But if the radius is different, it has a different potential. If the radius is different, it has a different potential. So the equipotential surfaces are like concentric circles, and the circle must have a small distance here, and again a big distance and a bigger distance as we make the equipotential surface. If you want to make the surfaces by equal potential difference, suppose this is like 5 volt and this is 4 volt and this is 3 volt. So यहाँ पे potential difference क्या आ रहा है? 1 volt का फर्क आ रहा है. तो 1 volt मतलब equal potential difference में अगर आप इक्विपोटेंशियल सरफेस को बनाना चाहते हैं तो आप इसमें डिस्टेंस बढ़ाते जाना, क्योंकि जैसे जैसे डिस्टेंस बढ़ते हैं तो पोटेंशियल बहुत ही जल्दी कम हो जाता है. और यहां पर हमने एक इलेक्ट्रिक फील्ड का फॉर्मूला देखा था. अगर आप पोटेंशियल डिफरेंस को कांस्टेंट रखना चाहते हैं तो जो डिस्टेंस आएगी E इंटू डेल्टा एल या डेल एल is equal to del V. So if you want to make this as constant, if this is decreasing, you have to make this increase. So electric field is decreasing away from the charge, so you have to increase the delta L so that you can make it continuously. Okay, so let's go to a negative charge. It will be similar, and if there are two positive charges, the equipotential surfaces, inside this, between these two charges, electric field lines are repelling, so there is very less electric field lines. So less electric field lines means it will bulge like this. Less electric field lines, it will bulge like this. So and you can, this is a type of electrostatic potential for two positive charge, and it's the same for two negative charges also. But when we talk about one positive and one negative, means an electric dipole, there is a difference in the equipotential surface. So equipotential surface for a positive and negative means an electric dipole. One surface is the equatorial plane itself. So the equatorial plane, the potential is 0 because here is plus kq upon r and here is minus kq upon r, and the total potential is 0. And here there is attraction between this, so more number of field lines will be here. Electric field intensity is greater, so length L will be smaller here, but L will be greater here. Like this, you can draw diagrams. So it is bulging outwards because where there is more electric field intensity and there is a crowding of electric field lines, and there the equipotential surfaces can be drawn as very close to each other. Okay, if it is a uniform electric field, then you can draw the equipotential surfaces as, plane sheets like this, and which are equally spaced. But if it is a non-uniform electric field, means there is an increasing electric field, then you must place the sheets, one more sheet you can make, and the sheet will be more closely spaced. So here the sheets are more, the equipotential surfaces are more close, because electric field is increasing. And if the electric field is decreasing, this you have to keep it far away, so that the distance here is smaller, and here the distance here must be greater. So that is a difference that you can go for equipotential surface for an increasing electric field, decreasing electric field, and a uniform electric field. For a uniform electric field, equal distance you can keep, and you can make thousands and infinitely many such equipotential surfaces, equipotential sheets. So that's all about equipotential surfaces. So the third topic is electric dipole in an external uniform electric field. But we are finding the potential energy. Last time we learned about torque exerted on an electric dipole placed in an external uniform electric field. That was in the first chapter. So this chapter we are learning about potential energy of such type. So there is a uniform electric field. I am going to represent it by parallel lines in this direction from left to right, and I am keeping one dipole at any arbitrary position. So this is dipole, and dipole moment is from negative to positive. So this is the direction of P cap, and this is the direction of E. And we already know what is a torque acting. Torque acting is PE sine theta, the magnitude of torque acting. So this is the magnitude of torque acting on an electric dipole. So what is the work done then? Because there is a rotatory motion. So when there is a rotational motion, there is a torque, means there is like a force, something. So force का जो rotational analog है वो है torque. So force and displacement is theta here, because the angle is changing. So force into displacement is work done. In the same way here, work done can be torque into displacement theta. But the force is depending on sine theta. So as the theta changes, the torque changes. So you have to go for a very small work done for a very small displacement. So very small work done for a very small displacement is this, tau into d theta. So the total work done, we know we can go for the integration, or from a particular angle to a particular angle. Theta initial to theta final, theta 1 to theta 2, whatever. You can write it initial or final. And put the value of tau here. Work done is equal to integration theta initial to theta final PE sine theta d theta. And your final answer is integration of sine theta. What is the integration of sine theta? It is minus cos theta. Theta initial to theta final. So minus P cos theta final to minus cos theta initial. So you will get here, if you keep this minus here, P cos theta final or P cos theta initial. So this work done according to work energy theorem. According to work energy theorem, work done is always equal to what? Work done is always equal to the change in energy. So this is a change in energy. So this is the final energy P cos theta F, and P cos theta I is the initial energy. So this is only change in energy, but if you want to find exactly how much is the energy, for that we will keep the initial energy to be 0. So in order to keep the initial energy to be 0, the theta must be 90 degree, because cos 90 is 0. So I am going to take theta initial to be 90 degree and theta final to be simply theta. So then what is the final formula? And the final formula is so work done is equal to minus P cos theta, and this is the potential energy of the system, minus P E cos theta, or I can write it like this, P dot E in vector form, P dot E in vector form. So the fourth topic that we are learning is dielectrics and polarization. So what do you mean by dielectrics? Dielectrics is a non-conducting material with no free charge carriers. Once again, what is dielectric? Dielectric is a non-conducting material with no free charge carriers. So metal is not a dielectric because it has free electrons in its outermost shell. So let's go to the next topic in this, that is polarization. So we are talking about the polarization of dielectrics now. So there are actually two types of dielectrics. One is a polar dielectric and other is a non-polar dielectric. So what do you mean by polar dielectric? A polar dielectric, if I represent like this, it has already, the molecules are already some dipoles. But the dipoles are being randomly arranged. So this is a polar dielectric. And another one is a non-polar dielectric. It's a non-polar dielectric because their charge centers coincide. So in chemistry, you learn in detail about polar molecules and non-polar molecules. That's the same concept here. So in physics, we are not going deep into the chemical structure or type of bonding or electronegativity and all those things. So if their charge centers do not coincide, then that is a polar type dielectric. And if they coincide, then that is a non-polar. So there is no separate pole here, but there is two separate poles. And when you keep this polar dielectric, a plastic-like substance, in a, means which is not conducting, and water is a polar dielectric. So if you keep it in an external electric field, what happens is the dipoles tends to align in this direction. The dipoles tends to align like this. And if a non-polar dielectric is kept inside, you are kept in a external electric field, and they also tend to develop poles. As their charge center, the positive will experience a force in the direction of electric field and the negative will experience a force in the opposite. The negative part will experience a force in the opposite direction of electric field, so you will get some induced dipoles here. So some induced dipoles. So a dipole is induced. So whether it is a polar dielectric or a non-polar dielectric, a net dipole moment is induced in the opposite direction of the given electric field. You know what is the electric field of this dipole? This dipole is in this direction. Positive to negative, positive, negative, positive, negative, positive, negative. Not dipole moment, electric field. So electric field of the dipole is from positive to negative. So there is an internal electric field which is trying to cancel the external electric field. So it means that inside this dielectrics, the electric field tends to reduce. So how much a material get polarized, that is another matter to discuss. So this is actually called polarization. When it is kept in an electric field, even though they have individual dipole moments, but the net dipole moment is actually here 0. But here the net dipole moment is not 0. And here also anyway there is no dipole moment at all. But there is a net induced dipole moment now. So what is the total dipole moment? How will you calculate? So how can you calculate the total dipole moment? So the total dipole moment per unit volume, or otherwise the dipole moment per unit volume, is directly proportional to, it is found that the dipole moment induced here is directly proportional to the electric field intensity, because the greater electric field is the external electric field and the greater will be the chance of aligning of the dipoles or induction of new dipoles. So अगर बाहर का इलेक्ट्रिक फील्ड थोड़ा ज्यादा ताकतवर है तो ज्यादा जो डाइपोल्स है वो बिल्कुल अलाइन हो जाएगा, लाइन पे आ जाएगी, या ज्यादा डाइपोल्स इंड्यूस हो जाएगी तो एक डाइपोल मोमेंट का जो इंटेंसिटी है उसका वैल्यू जो है वो बड़ा हो जाएगा. So it is directly proportional to the external electric field, and we can write it like is equal to chi into electric field. What is chi? Chi is called electrical susceptibility. It is read as chi, and chi E, because there is chi B also, means magnetic flux also has the same thing, susceptibility. So I will write this chi as electrical susceptibility of the dielectric medium. Electrical susceptibility of the dielectric medium. How the dielectric is able, how it is responding towards the external electric field. Is it ready to arrange all its dipole? Is it not ready? It is arranging only few dipoles. So it is the ability of the medium to respond towards an external electric field. That is a susceptibility, electrical susceptibility of dielectric medium. So it is not electrical permittivity, it is the ability to respond towards an external electric field. So it is electrical susceptibility of the dielectric medium. So that's all about the module number 6. So we have discussed the four small topics here, and the first topic was relation between electric field and electric potential, and then we discussed about equipotential surface. Then we discussed about the potential energy of a electric dipole placed in an external uniform electric field. And the lastly we discussed about dielectrics and polarization. So whether it is a polar or non-polar dielectric, we can still polarize it so that some internal electric field or internal dipole moment is there induced, and which produce an electric field, and that electric field tries to cancel the external electric field. So that's all about this topic, and in order to get clarified of whatever you have learned so far, so you have to do some questions in the exercise. Question number 12, 13, 14, 15 from the exercise. End of the textbook. And examples 4, 5, 6, 7. So do this 8 questions to get your topics clarified.